Welcome to Submodule 2 of Drillstring Design. In this submodule, our objectives are to understand drillstring failure modes under overload conditions, become familiar with criteria used to design and select drill strings and their components, and explain the factors influencing buckling and structural soundness. We won't cover fatigue design or detailed pressure considerations in this session. Those will be addressed in later submodules. Overload design ensures the drill string operates below its maximum rated capacity with appropriate design factors applied. The rated load capacity is the manufacturer's published limit, while useful load capacity is that limit reduced by the design factor. Key terms include overload, load factor, and overpull margin. For tension, the design factor, DFT, typically ensures the working load remains at or below 80% of the yield strength. For torsion, the torsional design factor, DFTR, protects against twist-offs by ensuring torque is limited to below the pipe's or tool joint's torsional strength. Burst and collapse design factors deal with differential pressure across the pipe wall. These constraints collectively create an operational envelope that maintains safety while maximizing usable strength. Loads in the drill string will vary considerably, dependent on the operation taking place at the time. The load cases above are what needs to be considered for competent drill string designs. DS1 and API RP7G identify 7 common load cases for drill strings: rotating off bottom, reaming, back reaming, rotary drilling, tripping in, tripping out, and slide drilling. Each case applies different stress combinations. For example, back reaming imposes higher torsion, while tripping out increases tensile load. In this directional drilling course, we narrow our scope to torsion and tension because these dominate drill string design. Pressure-related load cases such as burst and collapse will be introduced later. By focusing first on torsion and tension, we establish the foundation of overload design before layering in more complex load interactions. When we talk about overload design, the bottom hole assembly plays a role, but it is not usually the controlling factor. Drill collars and stabilizers are made from larger diameter, stronger material than drill pipe, which means they are less likely to fail under tensile or torsional overload. They also sit further downhole, away from the maximum stress location, which is usually in the upper drill pipe joints near surface. This means that a few extra stabilizers, or even an extra collar or two, don't make much difference to the overall overload capacity of the drill string. However, we still need to configure the BHA approximately before finalizing the drill string design. The reason is that the BHA contributes weight and drag, and this load is distributed across the drill string. For example, adding more heavyweight collars increases total string weight, which in turn increases tensile load at the surface. While it won't usually drive overload failure in the collars themselves, it affects design calculations for the pipe above. The key takeaway is that while the BHA doesn't control overload failure, it sets boundary conditions for the rest of the string. That's why we start by approximating the BHA layout before refining the design of the drill string. The overload design process follows a logical step-by-step approach. First, we set the design factors for tension and torsion, ensuring that the useful load capacity is a safe fraction of the rated load. Next, we calculate the loads the drill string will face: tensile, torsional, and equivalent von Mises stress. These loads are then compared against the design constraints. We also check the load factor, which is the ratio of applied load to rated strength. If the greatest load factor is below the maximum allowed, the design is acceptable. If not, adjustments must be made. The process also checks the overpull margin, the difference between maximum allowable tensile load and actual surface load. If this margin is less than the required minimum, the design fails. At this stage, we configure the BHA, specify the drill string, and run torque and drag models to simulate loads across the 7 load cases. If any load exceeds the constraints, we modify the drill string by changing grades, sizes, or configurations until the design meets all criteria. This iterative process ensures that overload design is robust and realistic. A thorough overload design must evaluate multiple load types. The simplest are uniaxial loads, where tension or torsion is considered separately. For tension, the useful design load is calculated from the design factor and the pipe's minimum yield strength. For torsion, the operating torque must be below either the pipe's torsional yield or the connection makeup torque, whichever is smaller. Burst and collapse loads are also checked. Burst is caused by higher internal pressure than external, while collapse is the opposite. Both require design factors based on the pipe's published ratings and the applied differential pressure. More complex are biaxial loads, where tension and torsion interact. Under torsional load, the pipe's tensile capacity decreases, and vice versa. Multiaxial loads add bending to the mix, producing stress combinations that are closer to real-world drilling. Connections must also be evaluated for tensile capacity under makeup torque. Modern software automates these checks, but understanding the principles ensures engineers recognize how different loads interact and where failure is most likely to occur. Let's examine uniaxial load cases more closely. For tension, the maximum design load is equal to the design factor multiplied by the pipe's minimum yield strength. The total surface tension is the buoyed weight of the drill string, which includes both pipe and collars. The margin of overpull is the difference between tensile capacity and actual surface load, and it must remain positive. For torsion, the design rule is that the applied torque must always be less than the smaller of two limits, the connection makeup torque or the pipe body torsional strength. For burst, we use the internal differential pressure, comparing it to the pipe's burst rating with an appropriate design factor. For collapse, we calculate the external differential pressure, accounting for annular pressure, internal mud column, and geometry. The design factor is the ratio of collapse rating to calculated collapse pressure, which must remain above 1. Uniaxial calculations are the starting point for overload design, but they tend to overestimate strength because real operations involve combined loading. That's why we move on to biaxial and triaxial design checks. Let's work through this tensile loading example step by step. We begin with the pipe's rated tensile load capacity, which is 311.4 thousand pounds. That's the absolute maximum strength based on its material properties. Now, we don't use that number directly. Instead, we apply a design factor to build in a margin of safety. In this case, the design factor is set at 0.8. So we multiply 311.4 thousand pounds by 0.8. That gives us a maximum design load of about 249,000 pounds. Next, we calculate the working load. That's the actual force expected at the surface. To do this, we take the buoyed weight of the drill pipe and the drill collars, meaning their weight after accounting for the lifting effect of the drilling mud. In this example, the working load comes out to 233.2 thousand pounds. Finally, we look at the margin of overpull, or MOP. This is simply the difference between the maximum design load and the working load. Here, it's 249,000 pounds minus 233,000, leaving just under 16,000 pounds of extra capacity available for unexpected loads. If a minimum MOP of 50,000 pounds is required, then it indicates we should move to a higher grade of pipe. Here we move from uniaxial tension to combined tension torsion. DS1 charts show capacity envelopes for each grade/size. Note the example. S135 carries approximately 660 kips in pure tension, but only approximately 580 kips at 40,000 foot-pound torque. The message is, you must check the interaction, not just catalogue axial ratings. In reaming/back reaming, both torque and axial load are high. Design margin must sit inside the DS-1 envelope for all planned modes. Pressure ratings are quoted at zero axial load, but real strings carry tension. Capacity drops with axial stress. The slide's example, S135 collapse rating approximately 6,200 pounds per square inch at zero axial load, but approximately 5,000 pounds per square inch under 300 kips tension. Same principle applies to burst. The point is not that collapse is common on drill pipe, but that your design check must couple pressure with axial load whenever differential pressures may be material, e.g. high weight fluids swabbing across a narrow annulus. If the combined point falls outside the DS1 envelope, increase the grade of the pipe or reduce the planned loads. Triaxial design requires somewhat complex algebra calculations and can be performed by hand or coded into a spreadsheet. However, to perform an analysis for multiple locations, it is much more effective to perform the analysis with a software program. Simulators allow us to model how the drill string will behave under the 7 key load cases defined by DS1: tripping in and out, rotary drilling, reaming, back reaming, slide drilling, and rotating off bottom. To achieve this, we need several critical inputs. First, the well trajectory, both the planned path and the most probable deviations caused by tortuosity. Doglegs and added curvature increase stress, so they must be captured realistically. Next, borehole and casing dimension. And included as changes in hole size affect drag and buckling potential. We also feed in mud density, which determines buoyant weight and hydrostatic pressures, and friction coefficients for both cased and open hole sections. Friction differs by formation type, mud system, and casing condition, so realistic values are essential. The simulator is then used to distribute loads along the drill string under these conditions, showing where torque peaks or where tensile stress approaches safe limits. Importantly, once drilling starts, simulators can be field calibrated by comparing predicted hook loads and torques with actual measurements. This improves accuracy and makes the tool dynamic, helping engineers update designs in real time. In short, a simulator is not just a planning tool, it's a living model that evolves with the well, ensuring overload design is not theoretical, but grounded in measured performance. Connections, particularly tool joints, are often the weakest points in the drill string. The pipe body itself may have very high tensile or torsional capacity, but the welded tool joints and their threads usually govern overall strength. Tool joints are manufactured from high-strength steels, usually with a minimum yield of around 120,000 pounds per square inch. However, API RP 7G specifies that most standard tool joints are only considered to have about 80% of the torsional strength of the pipe tube. This conservative assumption reflects the reality that threads, welds, and geometry introduce stress concentrations. Makeup torque is the critical operational variable. Each connection has a recommended makeup torque that provides sufficient preload to prevent loosening while maximizing strength. If under-torqued, the connection may unscrew during drilling. If over-torqued, the threads may be damaged or overstressed, reducing capacity. The recommended torque values are standardized in APIRP 7G and DS1, but proprietary premium connections may have different requirements supplied by the manufacturer. Following these values precisely is crucial. Torquing practices must use calibrated tongs or torque turn systems, not rough estimates. When we move deeper into overload design, there are 3 major considerations. First, tool joints are usually the torsional weak link. Even though the drill pipe tube may appear strong in tension and torque, DS1 and API RP7G assume most tool joints only provide about 80% of the torsional capacity of the pipe. This is because the threads and weld area act as stress concentrators, and torsional shear often initiates at these points. That's why torque checks must always focus on connections. Second, drill collar connections behave differently from drill pipe tool joints. Drill collars are much larger in cross-section and generally carry lower torsional stresses per unit area. As a result, they rarely fail in torsion. However, their dimensions and torque ratings must still be calculated, especially if collars are used in high-torque environments such as motor drilling or rotary steerable systems. Third, makeup torque must be tightly controlled. Correct torque ensures the connection is properly preloaded, distributing stresses evenly across the threads. If makeup torque is too low, the connection risks loosening and backing off downhole, a catastrophic failure mode. If too high, the threads may be overstressed or cracked, leading to reduced life. The overarching message here is that overload design is not just about body strength, it's about how the weakest elements in the system, usually connections, interact with real torque and tension loads. Managing these considerations is critical for a reliable string. On this chart, the connection pin neck tensile capacity versus makeup torque for different pin IDs. The dotted horizontal lines mark the pipe body tensile yield. To use it, start at our actual makeup torque, here 30,000 foot-pounds, on the x-axis. Go up to the curve for our pin ID, e.g. 3.25 inches for NC50. Go left to read the connection pin neck tensile capacity at that torque. Now compare that value to the dotted horizontal line for the tube's body yield. If our point lies above the dotted line, the tube would reach yield first. The connection is not the limiter. If it lies below, the connection governs. For S135 5-inch drill pipe, the tube's axial capacity at zero torsion is about 660 kips. That's the level represented by the relevant dotted line. At 30,000 foot-pounds and 3.25-inch pin ID, the intersection typically plots above that dotted level. Therefore, the connection remains stronger in tension than the tube at this makeup torque. The takeaway, the horizontal dotted lines equals tube body yield. Use them as a quick go, no-go check after you've read the connection capacity off the curve at your actual makeup torque. If your operating point is above the dotted line, tube governs. If below, connection governs. In this submodule, we explored overload design in depth. We covered uniaxial, biaxial, and triaxial loads, simulator requirements, and the critical role of connections and torque. The key message is that overload design balances body strength, connection limits, and operational controls. We'll continue with fatigue design next. Thank you. This concludes Module 2 of 4. Please progress to the quiz.